Everyone wants gas. It's clean, efficient, and with large reserves available, it will play an increasingly vital role in satisfying the UK's energy needs for a long time to come. In order to meet future consumer demand, Transco decided to increase the gas transmission capacity between the St Fergus terminal near Peterhead and the compressor station near Aberdeen. This would require a new pipeline. The laying of this 72-kilometre, 1.2-metre diameter, high-grade steel pipe would constitute Transco's largest ever capital spend on a single pipeline project. Only contractors who meet stringent quality, safety and environmental criteria can work on Transco projects. The design and build contract to construct this new pipeline was awarded to NACAP Lawrence. Although Aberdeenshire is mainly an agricultural area, the pipeline's 72 kilometres had to pass through a variety of geological conditions from very hard granite to waterlogged peat bogs. The challenges below ground were matched by those above ground, as the pipeline had to cross 6 rivers, 62 roads and a live railway line on its way south from the St Fergus terminal to Aberdeen.
This pipeline project is a major challenge to Transco in terms of safety, in terms of environment and in terms of the engineering challenges that we face over the next 2 to 3 years. It's going to take a great deal of teamwork by many individuals to take this project from concept, where we are at the moment, through to commissioning.
The first stage of preparation involved establishing and then protecting the site boundaries. After surveyors pegged out fence lines along the route, fencers then followed, installing the posts using a tractor, trailer and post hammer. Quad bikes proved very effective at quickly stringing out fence wire between the posts. The type of fence employed was always determined by the use of the adjacent land. As cattle were often present, barbed wire fencing was required to keep them off the site. Meanwhile, over 32,000 tonnes of 1.2-metre diameter pipe was shipped from the manufacturers in Italy to Aberdeen. The 70-kilometre pipeline required 6,000 sections of pipe. Averaging 12 metres in length, the pipes had a higher carbon content than traditional pipeline steel. This made the pipe stronger, allowing it to carry greater pressure, while reducing the thickness of the material. The result was a large reduction in the weight of the material being transported. Nonetheless, it still took... Meanwhile, over 32,000 tonnes of 1.2-metre diameter pipe was shipped from the manufacturers in Italy to Aberdeen. The 70-kilometre pipeline required 6,000 sections of pipe. Averaging 12 metres in length, the pipes had a higher carbon content than traditional pipeline steel. This made the pipe stronger, allowing it to carry greater pressure, while reducing the thickness of the material. The result was a large reduction in the weight of the material being transported. Nonetheless, it still took 20 shipments to bring it all in. This in turn required a fleet of lorries to make 2,000 trips, transferring the pipes from the harbour to pre-constructed storage areas. On arrival at the storage area, each pipe was thoroughly checked for damage before being carefully stacked. Once the boundaries of the pipeline were established, topsoil had to be stripped from the land before the heavy construction plant could begin work. The soil was pulled back from the fence by tracked excavators. carefully stripping to a depth consistent with the varying thickness of topsoil, leaving the site surface at subsoil level. During this process, Transco stipulated that an archaeologist be present to investigate areas of archaeological interest. Any significant finds were passed to the county archaeologist for further investigation.
This is a worthwhile process because it enables us to assess the archaeology that's in the area, but also perhaps more importantly to discover hitherto undiscovered sites and excavate them and preserve them by record.
The excavation of trenches and the general construction process can result in the destruction of land drains. Although these were to be replaced at the backfill stage, they would cause the trench to flood during periods of wet weather. To alleviate this problem, pre-construction drainage was installed immediately before or after the topsoil was stripped. A header drain was installed, the end of which was connected to an existing outfall, or where this wasn't possible, new outfalls were constructed to take the accumulated water to a local watercourse. Any existing drains found were connected to the header to keep the excavations free from water. Under the strict guidelines set out by the government, Transco were obliged to construct the pipeline without damaging the environment. As a result, an environmental impact assessment was carried out at the planning stage. This was supported by close liaison with environmental agencies to ensure that all possible measures had to be implemented to preserve the lives and habitats of local wildlife.
Which sections we're going to be doing first?
Major points of concern were thus identified early and addressed during the project design phase. Where possible, environmental damage was avoided by rerouting the pipeline or by implementing strict control measures. For example, sand martins nested in the sandy soil of the trench sides and the soil stacks. In these areas, trenches were left open and topsoil was not replaced for several weeks after the main activities had passed by. This ensured that the ground was not disturbed until after the birds had moved on.
It's very nice to see how protective the men are of the sand martins. They view them very much as their birds, their nests, so they're very protective. It's a good combination.
Two of the main concerns were firstly the collection of groundwater in open trenches containing excavation silts, and secondly, water running off the working areas during periods of heavy rainfall. If these waters were released into a watercourse, it could have had serious consequences for vegetation and fish stocks. Consequently, Transco worked hard to combat silt-laden water and successfully met the rigid standards set by the government's Environmental Protection Agency.
I think the most satisfying outcome of this would be to come back in 5 years' time and for nobody to know that Transco had laid a pipeline across 50 miles of Aberdeenshire countryside.
Before excavation could begin, a series of trial holes were drilled along the centre line of the pipe. This highlighted areas of rock that could not be excavated by traditional methods. Once identified, a specialist team of subcontractors were commissioned to blast the rock areas. Hydraulic track-mounted drill rigs drilled holes for the charges at 100-metre intervals. Linking the detonations with a very slight delay between each one minimised the effect of the blast on the surrounding area. Lorries transported the pipes from the storage areas to the site access points at locations where the pipeline crossed larger roads. It was vital to load the pipes onto the lorries in the correct order to ensure that heavy wall pipe and the bends were offloaded in the correct place for the subsequent construction. If the ground conditions on site were soft, the pipes were transferred from the lorries to purpose-built tracked pipe carriers. The pipes were then transported down the site and offloaded along the predetermined line.
With over 1,000 people involved in this pipeline project, obviously teamwork is vital. Subcontractors have been brought in for all the specialist operations, and although local labour has been used wherever possible, the huge pipeline team has got a truly international feel.
After the pipes had been strung out, the contractor's mainline welding crew welded together as many pipes as possible above ground. Breaks in the mainline were left for obstacles such as road, river or service crossings, or awkward bend configurations. Prior to the front-end welding, a machine suspended from the arm of a side boom was fitted onto the end of the pipe. Its rotating cutting heads profiled the pipe face, ready for the automatic welding process. The first run of the welding process, the root, was done internally. The lead pipe was set on skids with the internal welding machine inside. The second pipe was then lined up and the machine brought forward to locate the joint automatically. During this, the machine also acted as a clamp to hold both pipes in place. The welding was then done by 6 internal weld heads. Once the root was complete, the second pipe was lowered onto the skids and the process repeated. Following on behind this was the back end of the mainline welding train, consisting of 6 external welding stations that filled out the gap between the bevels.
The most satisfying part regarding the welding is the repair rates has now dropped down to single figures. The welding crew are working well together. We have a combination of Italian, Spanish and Scottish. They're all working extremely well. The repair rates are very good.
All welded joints in the pipeline were subject to 100% inspection. This is normally done using radiography. An X-ray source mounted on a crawler unit travels along the inside of the pipe, locating itself on each weld. A small controlled amount of radiation passes through the weld and leaves an image of the weld on the photographic film placed around the outside. The films were checked at the site compound for welding defects. Any areas of concern or defects were highlighted for investigation and repaired on site. On this project, additional inspection by automatic ultrasonic testing was carried out back-to-back with X-ray testing to assess its use as a safer alternative. Immediately behind the front welding operations, the welds were checked by fixing the UT machine to the same band that the welding machines were fixed to, thus enabling the machine to rotate around the welded joint. The machine consists of a number of sensors, each of which sends an ultrasonic pulse into the weld to a predetermined depth. The weld integrity affects the speed and direction of each pulse. The results were relayed to the operator's vehicle and viewed graphically on the computer screen and stored electronically for future reference. The trial was so successful that this technique replaced X-ray testing as the inspection method used for all mainline welding.
The biggest advantage we've found so far on this project is the use of the ultrasonics for getting almost instant results back from the weld testing.
After each welded joint had been accepted, a fusion-bonded epoxy coating was applied. Prior to coating, the joint was cleaned by grit blasting to remove any rust or scale deposits. An induction coil was then placed around the joint to heat it to 250 degrees centigrade. Epoxy powder was sprayed onto the joint, the heat of which fused the powder onto the blasted metal. Once the coating had cooled to ambient temperature, it was then checked for pinholes and defects by applying low current, high voltage Holiday detection methods. A pipeline of this scale inevitably raises important health and safety issues. Deep excavations, heavy plant and machinery, large pipes and pipe strings, overhead power lines, and the fire risk from welding operations all contributed to an increased potential for danger on site. To combat this, a project health and safety plan was compiled prior to the start of the construction phase. This document identified the statutory responsibilities of the client and contractor and outlined the control measures to be adopted to ensure the health and safety of the workforce. Two particular safety issues on pipeline projects include deep excavations and the control of plant and machinery working below overhead power lines. Both of these areas were monitored closely by Transco site staff throughout the project.
A strong safety culture can only be improved by continual education and training. On this project, Transco introduced a new initiative called BOSS. That's the Behavioural Observation Safety System, introduced to ensure that all staff on the project were adequately trained and qualified for the tasks in hand.
After the pipe had been welded and coated, the main line was ready to be excavated. Each excavator had a banksman to assist the operator in checking depths and to warn of any hazards. Throughout the project, excavators always tried to work in an uphill direction to allow any ground or rainwater to run away from them. On average, 750 metres of excavation was achieved daily. During the excavation, naturally occurring groundwater was encountered in areas with a high water table. To overcome this, the height of the water table was reduced by installing either well point or deep well dewatering methods. Both systems involved installing slotted pipes known as vertical wells to a predetermined depth and coupling these to a suction pump. This removed water from the ground to a header system and onto an approved discharge location. Since this water was clear, it could be discharged directly into a local watercourse. The flow of the discharge was controlled by baffle plates to stop the water causing silt pollution by scouring the bed and banks of the watercourse.